Students, in this note set, we're going to take a look at a way to represent atoms with regard to their electrons called dot diagrams. And we're going to look at how atoms as a way of understanding their electron ownership through dot diagrams, how they bond together. First, we know from earlier when we studied modern atomic theory about Bohr diagrams. Bohr diagrams show the total number of electrons possessed by an atom when it's in ground state and it's neutral, and it shows each ring as being one of the principal energy levels. So the first principal energy level can hold up to 2 electrons, and that's why in these diagrams the first ring around the center dot is the nucleus. The first ring around that can hold up to 2 electrons, and then the second ring around that can hold up to 8 electrons. Well, we were able to draw Bohr diagrams for every element from hydrogen through argon. And I said, don't worry about elements beyond argon. And that's going to hold true when we consider dot diagrams as well. What I want to draw your attention to with these Bohr diagrams is the outer ring. For every single element drawn here, there's a certain number of dots in the outermost ring. So for instance, lithium in its outer ring has 1 electron. Beryllium in its outer ring has 2 electrons. We're only looking at the outer ring. Boron has 3 dots in its outer ring. Carbon has 4, 5 for nitrogen. If you count them up, 6 for oxygen, 7 for fluorine, and 8 for neon. And in the column below, right below that same element, you'll see the same number of dots in the outer ring. Now that's not an accident. Those electrons in the outer ring, we give a special name to because those are the electrons that actually participate in chemical bonding. We call them valence electrons. Electrons in the outer shell of an element's Bohr diagram. And the reason they're in the outer shell of the Bohr diagram is because they're in the outer shell of the element's principal energy level. Those electrons, the ones that are accessible to other atoms, are the electrons that will participate in bonding. The way we show the number of valence electrons, since students, if you get to argon, you've got 18 dots. Let's say we just want to show the outermost dots. Well, we write the element symbol and we put the appropriate number of dots around it. So for example, nitrogen, it has 5 valence electrons, 5 dots in the outer ring of its Bohr diagram. To make a dot diagram, we simply put the letter N, nitrogen's chemical symbol, with, if you count up the number of dots, there are 5 dots around it. Each of those dots represents 1 valence electron. It does not matter where you put the dots around the chemical symbol. So this is just as good as the other dot diagram, which is just the same as this one, which is just the same as this one. It doesn't matter where you put the dots, but it does matter how many dots you put around the chemical symbol. Elements within a group on the periodic table, that would be a vertical column, they react similarly. And if it's the valence electrons that determine how an element reacts, well, guess what? They all have the same number of valence electrons in a vertical column. So here's the elements number 3 through 18. Lithium is in the same column as sodium. They both have the same number of valence electrons and the same number of dots in their dot diagram. Beryllium is in the same column as magnesium. They both have 2 dots in their dot diagram, indicating 2 valence electrons. Boron and aluminum are the same. Carbon and silicon are the same. Nitrogen and phosphorus, oxygen and sulfur, fluorine and chlorine, neon and argon. They all have the same number of valence electrons, and the same number of dots. Now, if we were to count the number of dots from left to right in the periodic table, and we're skipping over the transition metals here, but if we go from left to right in periods 2 and 3, the number of valence electrons are 1, 2, 3, all the way up to 8. 8 valence electrons is the number of dots, or the number of valence electrons that noble gases normally have. There is an important exception to that, and we'll talk about that at the end of this note set. Okay, so notice that noble gases, neon and argon, have 8 valence electrons, 8 dots in their dot diagram. Also, you probably recall this from earlier classes, noble gases don't bond with other elements. The reason they don't bond is because they're already stable. They have no need to achieve a different energy state than they already have because they're already super stable as it is. And the underlying reason, and now we're ready to kind of lift up the hood and see why, is because their s and p orbitals are filled. Take a look at this. If we were to draw an orbital diagram for neon with 10 electrons when it's neutral, it would look like this. The 2s and the 2p orbitals in its outer principal energy level are filled. Argon has an orbital diagram like this when it's neutral. Notice that the s and the p orbitals of its outer principal energy level, in this case the third principal energy level, are full. That means they are super stable. They have filled principal energy levels. And as we've noted over the centuries of observing chemicals and how they react, extra stability is found whenever an atom has access to 8 valence electrons. There's something special about having 8 valence electrons. We give a name to this special property. It's called the octet rule. And it goes a little bit like this. When atoms bond, they're going to bond so as to attain 8 valence electrons. They want to get 8 electrons. Now, sometimes we use the term happy to describe an element. Either it's happy in this bond or it's not. And, of course, elements they don't have feelings, but what we mean when we say happy is that they are energetically stable or not. And if they have access to 8 valence electrons, then they are stable and they are happy. Let's look at some examples. Neutral chlorine has 7 valence electrons. And we know that a chlorine molecule consists of 2 chlorine atoms bonded together. When they bond together, the 2 chlorine atoms each share one of their electrons in a covalent bond. Remember, covalent bonds are formed when 2 nonmetals bond together, and an ionic bond is formed when a metal bonds to a nonmetal. So when 2 chlorine atoms share an electron in a covalent bond, both of those atoms will have access to 8 valence electrons. Take a look at this. So the neutral chlorine atoms, if you count up the number of dots around them, you'll find that there are 7 around each. When they form a chlorine molecule and share an electron with the other atom, now they have access to 8 valence electrons. They are energetically stable now that they have this arrangement. Let's take a look at another one. This one's a little bit tougher. Neutral nitrogen atoms each have 5 valence electrons. When 2 nitrogen atoms bond together, they share 3 electrons each. They form a covalent triple bond. And when that happens, both of the atoms have access to 8 valence electrons. So if you count the number of dots around either individual nitrogen, you would see 5. When each nitrogen atom shares 3 of the 5, then if you count up the dots in between the two atoms. 1, 2, 3, 4, 5, 6, 7, 8, and 6 in the middle are shared. 7, 8 for the other nitrogen atom. Both nitrogen atoms are stable because they have access to 8 valent electrons. The cool thing about the octet rule is it doesn't just allow us to describe the formation of covalent bonds. We can also think about ionic bonds. First, let's talk about stable ions. If we want to form a stable ion, the atom needs to have access to 8 valence electrons. So take oxygen. Oxygen, when it's neutral, has 6 valence electrons. To become a stable ion, it's going to gain 2 more. So instead of 6 electrons, it would have 8. Take a look at the orbital diagram for neutral oxygen. It wants to fill this 2p sublevel, but it's missing 2 arrows. There's a space for 2 more arrows here, meaning electrons. Aha! When oxygen fills its 2p sublevel, it would gain, remember, electrons are negatively charged. If you gain 2 electrons, then your charge becomes 2 minus. Compare that to fluorine. Fluorine, when it's neutral, has 7 valence electrons. Here's neutral fluorine's orbital diagram. When it forms an ion, it's going to gain just 1 more electron to fill its 2p sublevel. And by gaining 1 electron, fluorine's charge becomes -1. Okay, so we add the number of electrons needed in order to reach an octet. What about losing electrons? Ions can also lose electrons to attain an octet of valence electrons. Let's consider sodium. Sodium has just 1 valence electron. To form its closest stable ion, its closest octet, it's easier for sodium to lose its 1 valence electron than for it to gain another 7 to give it 8. Here's neutral sodium's orbital diagram. Notice it has 1 electron in the 3s sublevel. If it just loses that 1 electron, it attains a filled 2s and 2p sublevel. It's the same as neon's electron configuration with 10 electrons, 10 electrons total, 8 of which are valence. By losing a negatively charged electron, sodium got a +1 charge. How about magnesium? Magnesium has 2 valence electrons. When it's neutral, it would have a total of 12 electrons, 2 of which are valence, or in the outermost principal energy level, the 3rd principal energy level. To get a stable octet, magnesium can either gain 6 electrons, or it can just lose the 2 electrons it has in its outer principal energy level. Turns out it's a lot easier for magnesium to lose 2 electrons than to gain 6. And just like sodium, it now has a filled outer principal energy level by getting rid of the outermost of its principal energy level. It got rid of 2 electrons, which provided a 2+ charge. Getting rid of negative charge particles gives you a positive charge. All right, now let's go back to the periodic table. We know from earlier, and I just had you memorize this pattern of charge, but now we can answer why. Why do all of the elements in column 1, when they form stable ions, have a +1 charge? Why do all of the elements in column 2 form stable ions with +2 charge? If we jump over the transition metals, we get to column 13 or column 3 in the old numbering scheme. They get a +3 charge. The carbon column and nitrogen column don't usually form ions, but if they did, it could be +4 or -4 for the carbon column, -3 for the nitrogen column, -2 for the oxygen column, and -1 for the halogen column. Every single charge for one of the stable ions results in an octet for that element. That's why we see this pattern. Okay, we know that when metals and nonmetals bond, they form ionic compounds. And we know that when they form ionic compounds, the compound's charge is neutral overall. That is, the sum total of the positive charge is canceled out by the sum total of the negative charge. Let's consider this in light of the dot diagrams that we've just taken a look at. How about when sodium bonds to oxygen? We know that two sodium ions, each of which have a +1 charge, are needed to cancel out one ion that's double negative in the case of oxygen. When they form an ionic compound, it's neutral and it takes the formula Na2O. Each sodium atom donates one electron to oxygen. Now, let's see what that means in terms of dot diagrams. Sodium, if you recall, has one valence electron, and oxygen has 6 when neutral. So here's neutral sodium, here's the other neutral sodium atom, and here's neutral oxygen. The two sodium atoms are each going to give, not just share, but actually give up their one electron to the oxygen atom. And the result is two sodium atoms, which once they've given up that one valence electron, you don't need to draw 8 dots around it. We know that it now has attained a neon electron configuration. But the oxygen atom now has a full 8 dots around it and a 2- charge. Another way to look at it is through the orbital diagram. Each sodium atom has one electron in the 3s sublevel. If each of the two sodiums donates that one electron to the 2p sublevel of the neutral oxygen atom, the oxygen atom now has a filled p sublevel, and sodium has an empty third principal energy level. Here's another example. Let's take a look at lithium when it bonds to fluorine. We know that when lithium bonds with fluorine ions, you've got one lithium with a +1 charge and one fluoride ion with a -1 charge. The compound lithium fluoride is neutral, of course, and it consists of one lithium and one fluorine atom. When they form that compound, the lithium atom donates its one electron to fluorine. Let's take a look at a dot diagram. Here's neutral lithium with its one valence electron. Here's neutral fluorine with its 7 valence electrons. If lithium just gives its one valence electron to fluorine, both atoms are happy. And when we say happy, we mean stable. So lithium now has lost its one valence electron and has gained a +1 charge because it gave up a negatively charged electron. And fluorine now has 8 valence electrons, and by gaining the one electron, it has a -1 charge. That's a stable compound. Let's look at it in terms of orbital diagrams. Lithium has a total of 3 electrons, one of which is valence. That's why there was one dot in the dot diagram. Fluorine has a total of 9 electrons, 7 of which are valence, or outer electrons. That's why there's 7 dots around fluorine, not 9. In the transaction to form the ions of opposite charge and thus make them attract each other, the lithium is going to donate its one valence electron to fluorine, and it will allow fluorine to fill its 2p sublevel. Here's the resulting orbital diagrams. Now lithium has given up its one valence electron. What's left, this is interesting. What's left is the 2 electrons in the 1s sublevel. And let's return to that in just a moment. Fluorine now has a completely filled first and second principal energy level. It's very stable. Okay, I know what you're thinking. Wait a minute. At this point, lithium, now it's gone from the second principal energy level down to the first principal energy level as being its outer valence electron level. Shouldn't it require 8 valence electrons? It only seems to have 2. Aren't stable ions supposed to have the 8 electrons that the octet rule demands? Aha. There are exceptions to the octet rule. Now, it's not very many exceptions, but they are very important and commonly seen, so I need you to pay close attention. Primarily hydrogen, but in addition to hydrogen, elements number 2, 3, and 4, helium, lithium, and beryllium, can be stable by having just 2 valence electrons. 2, not 8. They call this the duet rule, because think about this, students, in the first principal energy level, you can only fit up to 2 electrons, whereas in the second principal energy level, you could fit up to 8. That's why it goes 2 and then 8. Here's a picture of the formation of neutral hydrogen molecule. You've got a hydrogen atom with 1 valence electron and another hydrogen atom with 1 valence electron. If they were to form a compound, H2, they would share their 1 valence electron. Now, what we've seen before was that in the bond, each atom had access to 8 electrons, but here it's not 8, it's 2. Each hydrogen atom has access to 2 valence electrons and is stable anyway. The other atoms, besides hydrogen, and then sometimes when they form ions, helium, lithium, and beryllium, that don't always follow the octet rule, are those elements that are larger than calcium. Or even, let's limit our dot diagrams to just the first 3 rows of the periodic table. So elements 1 through 18, stopping at argon. Those are the only ones that we're going to draw dot diagrams for. Beyond that, things get complicated, and the octet rule is not always followed. Let's take a look at a couple of examples showing the duet rule in action. We know that hydrogen, when it's neutral, has 1 valence electron. Bromine, when it's neutral, has 7 valence electrons. When hydrogen bonds with bromine in a covalent compound, bromine will have access to its normal 8 valence electrons. It'll follow the octet rule. But hydrogen, since it only needs 2 electrons to be stable, will follow the duet rule. Take a look. Here's neutral hydrogen. Here's neutral bromine. When they form a bond, they each share 1 of their electrons. The hydrogen, after sharing, has access to 2 valence electrons and is stable or happy. Bromine now has access to 8 valence electrons and is also stable or happy. How about another one? Hydrogen bonding with sulfur. Now this time, hydrogen has 1 valence electron. Sulfur has 6 valence electrons when it's neutral. We're going to need more than just 1 hydrogen atom. We need 2 atoms of hydrogen in order to satisfy the octet rule for sulfur. Well, that's no problem. When 2 atoms of hydrogen each share 1 of their electrons, sulfur now has access to 8 valence electrons, and each of the hydrogen atoms has access to 2. Here's a nice equation showing this. 2 hydrogen atoms with 1 valence electron each, plus a sulfur atom with 6 valence electrons, will form a bond so as to share 1 electron with each of the 2 hydrogens. After sharing, the 2 hydrogens each have access to their 2 electrons, satisfying the duet rule, and sulfur has access to its 8 valence electrons, satisfying the octet rule for it. Okay, one last note. When we've talked about the duet rule and octet rule and dot diagrams, we've been shifting between ionic compounds and covalent compounds. So I just want to make sure that we're all on the same page. Ionic compounds are those where an electron is transferred from one atom to another. It always consists of a bond between a metal and a nonmetal. So for example, here's sodium transferring an electron to chlorine, and the result is sodium chloride. Here's calcium transferring one of each of its valence electrons to chlorine to form calcium chloride. Covalent compounds are formed when two or more nonmetal elements are sharing electrons, not transferring, but sharing. So how about hydrogen chloride? When hydrogen shares its one valence electron with chlorine, both atoms are happy. Hydrogen satisfies the duet rule, chlorine satisfies the octet rule. Do keep in mind that in an ionic compound, there's a transfer of electrons. Represented here is just one transfer of an electron, but you'd have billions and billions of atoms doing that same transfer. And you end up with a crystal lattice, a potentially infinite number of atoms bonded together in a particular ratio. And the ionic compound formula just lists the lowest whole number ratio of atoms. In a covalent compound, you have a specific number of atoms in each molecule, but you could have a collection of many billions of molecules. It all depends on how large your sample is. So when we show chlorine and bromine, those are two nonmetal elements. When they bond together, they're sharing electrons, and they have, in particular, one atom of chlorine and one atom of bromine in each molecule. So the formula reflects the exact number of atoms of each type. So if we know something about when a metal bonds to a nonmetal, and we know something about what happens when two or more nonmetals bond together, you might be wondering, well, what happens if two or more metals bond together? Well, this is where it gets a little bit weird. Metals don't hold on to their electrons strongly at all. In fact, it's a very, very weak electronegativity for any of the metals. Instead of possessing their valence electrons, metals, when there are a collection of, let's say, many thousands of metal atoms together, they just share all of their electrons. It's not a particular number. They're not sharing one valence electron with the next atom over. They just have a bunch of electrons, and since they don't attract them very strongly, they just share all of them. And that's why metals are such good conductors of electricity, because if you're sending a pulse down a copper wire, for instance, you've got to have electron movement. And when the atoms that originally brought those electrons to the collection don't have strong ownership of the electrons, it's much easier to send a pulse down the wire.